Hi everyone, welcome back. In this video we are going to talk about the classification of binary codes. So binary codes are the basic language of all digital systems. But these are not all the same. They are different types used for different purposes, like representing numbers, letters, and even for error checking. In this video I will explain how binary codes are classified and where each type is used. Let's get started with the basic and build up from there to big. Before seeing the classification of binary codes, let us understand what is meant by binary code. So it is a way of representing letters, characters and numbers using zeros and ones. So in our day-to-day life we are writing simply. Suppose if you want to write hashtag, so we can write with on the paper. It's very easy, but computer cannot understand like simply, so it has to convert into some other form in the form of zeros and ones. So how we will see how that classification happens inside the computer, so using with the help of binary codes. Basically, the binary codes has divided into two parts. So the first part is numeric. So second part is alphanumeric. Everything in the computer will be stored as zeros and ones. So if you classify binary codes, so first one is numeric. So if you consider the numeric under, so the numbers, basic 1, 2, 2, 3, 1, 2, 0 or any numbers in numbers. So alphanumeric. So the special characters we can say simply like capital letters, hashtag, at the rate, ASCII, these and all things, plus minus also, the space also, these and all things are come under alphanumeric. So alphanumeric we can understand that is a special characters. So for numeric we have like numeric means normal digits. For normal digits computer can understand like 12 is binary. So in decimal that is 1100. So 23 means 10111. So likewise we can store any decimal number by converting binary to decimal. So but for alphanumeric like special characters, so ASCII, so this is means American Standard Code for Information Interchange. So this is a generally American based union. So there they will decide throughout the world that what symbol what we have to use, what code we have to use. So as you're seeing that this is the ASCII table that the foundation has put in. So basically you are seeing the special characters starting from 32. So 32 represents the space and so on. Likewise you can see the numbers also from 0 to 9 have ASCII values, like 0 has 48. So if you see at the rate that is 64, and you can see that small a 97 and capital A that is 65, and that normal digits, spaces, open brackets, close brackets, and any digit has been represented here. So this is the fundamental use. So we can convert the decimal part to binary part and we can store in the computer. That is a simple method to store in the form of zeros and ones, the special characters. That is alphanumeric. Yeah, in alphanumeric that is decided by the ASCII Foundation. So in numeric also we have some kind of that is binary coded decimal and gray code, XS-3 code. These are some of the examples of numeric, and there are many more examples. Not examples, there are many more types of representing the numeric type. So we can see one by one how to represent the numeric system types. In the numeric part, so first we are going, this is numeric is very important. So in the numeric part we are going to see the first one, that is 8421 BCD. So let's see what is the full form of BCD. BCD means binary coded decimal. So in our day-to-day life we use normal that 1 to 10 or 1 to 7, that is binary to decimal or decimal to binary. If you observe there, you can see that 0 is 0, so 1 is 0001, 2 is 0010, and likewise 91001. Likewise this is a normal conversion. So if you don't know the normal conversion, you can check out our videos that I am giving in the description, and you can check in the iCards as well. Okay, that conversion I know. Then what is meant by 8421? Basically 8421 is nothing but the weight of the individual digit or the weight of the individual place. So I have written there, that's weight corresponding to the position. So if you observe 6, so that is 0110. So where there is ones, so according to ones you have to multiply with 1 and you have to corresponding add the position. Then after adding you can get the 6. So if you observe 4 plus 2, that is 6, In the fourth position we have 1, in the second position we have 1. So that is normal, 2 power and 1, 2 power 2, 1, 2 power 2, 2 power 3, 2 power 4, like that. And this is one of the famous representation, that is 8421 BCD, binary coded decimal. So if you observe the second example, if you want 9, so that 8 plus 1, that is 9. So this is one of the representation. In spite of those two, we have another some of the representations of BCD. So those are 2421, 5421 BCD. So let's check out these two as well. Up to now you have understood. So what is meant by weight? So weight is nothing but the place that we have to multiply with 1. So we saw up to now that is 8421 BCD. So according to 8421 we have to multiply the corresponding and we have to see that is weighted or not. So we have two types in numeric. So these and all things up to now we have saw in numeric only. So there are many types in numeric. So first one is weighted and second one is non-weighted. So we will see some examples also in this. These are the examples of weighted codes in numeric: 8421, 2421, 5421 BCDs. And in non-weighted codes we have XS-3 and gray codes. So if you don't know about XS-3 code and gray code, so don't worry, in this video we are going to discuss in a brief. So in the further videos also we are going to discuss in detail in the upcoming videos. So we have already saw 8421 BCD. So in the weighted codes only, the second one we are going to see is 5421 BCD. So I said that is weighted. So if you add two positions or any multiple positions, so we have to get the corresponding decimal. So if you see first 0, so all zeros. So if you see the ninth position, so you can add 5 plus 4. So in the position of 5 and 4 you can place 1 and 1, and remaining two positions you can place zeros. So that is the code. So likewise you can check any of the code. So if you want 4, so the 4 is available directly, place 1, remaining all zeros. So that's the simple representation, that is 5421 notation of BCD, binary coded decimal. The next one is we are going to see, that is 2421 BCD. So this is also the weighted one. So we have to multiply with 1 and the position, so that we have to get the decimal corresponding to that. So if you want to 9, so if you can add 2 plus 4 plus 2 plus 1, that is 9. So we have to put all ones in the places. So if you want suppose 3, so you can add 2 plus 1 according to the place, so you can get 3. Likewise if you add any digit, so you have to get corresponding decimal. So that is our 2421 BCD, that is binary coded decimal according to the weights. Up to now we have saw 3 types of BCD. Those 3 types are weighted, we know up to now. So what type of weighted? So they are weighted, they are under numeric, but all these are positive only. So the weight of the digit or the position is up to now we saw is positive. So those are called positive weighted codes. We have another type of representing the binary coded decimal or binary codes. So that is a negative weighted, means the position corresponding to the weight is negative. So as you are seeing there, 8, 4, minus 2, minus 1, this is the negative type of weighted things. So if you want any digit, like if you want 9, you can add all 8 plus 4 plus minus 2 plus minus 1 gives you 9. So whatever the number, so if you want 1, so you are going to add 4 minus 2 minus 1. So that is 4 minus 3 is equals to 1. So you are going to put in the down only, that is under the 4, under the minus 2, under the minus 1 ones, remaining are zeros. So likewise this is the negative weighted binary coded decimal. As represented, that is negative weighted codes only. We saw weighted, that is 3 types already we saw up to now. So it is nothing discussion more about non-weighted codes, because XS-3 code and gray code we are going to cover in upcoming videos. But so non-weighted means just means the weight doesn't follow the position, or so that the positions will not be measured with the help of. So that's a simple definition I can say. So if you move further, the next type in the numeric type is the sequential. So the examples under this is 8421 BCD, so that we have already saw. So again we are going to see that. So XS-3 code as well. And one more important thing in the 8421 BCD, so the general BCD, so that is if you add any digit 2 with the help of 1, so you are going to move to the next step. So if you add 1 to the 0, so you will be going to move to the next step. So if you add 1 to the 2, so you are going to get 3. So likewise, if you add any consecutive bits, so you're going to get the next digit only. So that is why this is known as sequential code. We have also two examples. So I have written there two examples. So 8421 is completed. So it is proved also. So next, the example is XS-3 code. So what is meant by XS-3 code? So if you add 3 or that corresponding to the in decimal and as well as binary also, if you add 3 in as 0011, so it will become the normal code will become as XS-3 code. The name itself indicates the pronunciation. XS means adding 3. 3 is more, so that is known as XS-3 code. Why? So after adding 3 also we are going to get as a sequence. So if you add any two consecutive bits, so you are going to get the next bit only. So if you add 1 to the first 0 corresponding 0011, so you are going to get the next one only, that is as 4. So likewise, if you add any consecutive bit with 1, you are going to get the next digit. So this is similar. So that is why they took as XS-3 and 8421 BCD in the sequential circuit. I hope you understand the sequential code. Moving ahead, in the numeric part only, we have another type of that code representation, that is cyclic code. So in the cyclic code, we have an example, that is a gray code. So let's see some of the gray code. Gray code means the successive code differs from each by 1 bit position. So the gray code is also known as the unit distance code, or you can simply say it is a 1 bit change only. So if I have put a table there, so you can observe. So 0 is 0 normal only, but in place of 1, so we are going to get 1 only. So the last most bit, the LSB least significant bit, is only changed. So for 2 also we are going to change only for 1 bit, and for 3 to 4 also we are going to change only 1 bit in the gray code I am saying. So I hope you understood. We are going to change only one position. More than one position we should not change in the gray code. That is the rule of gray code. So you observe clearly, then you can able to understand the difference between binary code and gray code. So only 1 bit change. So that is why gray code is known as 1 bit change. We have another example in the numeric only, that is self-complementing code. Complementing means inversing. So let's see. So we have examples also, 8421 BCD and XS-3 code. So these two already we have saw in the examples of sequential code. So in this also we have complementing code also we have. So in the previous one, cyclic code, so those are repeating. So cyclic means only 1 bit change. So that is why it is known as cyclic code. So why this is known as self complementing code, these two? So let's understand the name itself, the complement, how the name gets. So let's understand from that. We have the normal decimal digits from 0 to 9. So in this we want the 9's complement of n. So what is meant by 9's complement of n? So the formula is nothing but 9 minus n. So in the place of 0, so you are going to just subtract 9 minus that variable, that is n, 0. 9 minus 0 is 0. 9 minus 1 is 8. So last one is 9 minus 9 is 0. So I am going to get, I have highlighted it in the blue color as well, that is the complementing 9's complement of n for the decimal from 0 to 9. Similarly, if you observe in the XS-3 code also, so what is meant by XS-3 code I have discussed earlier only. So if you add 3 to the normal BCD, so you are going to get XS-3 code. So in the XS-3 code also, if you see the 0 and 9, so if you just complement the 0, you are going to get 9. Complement means, so 0011. so you have to invert zeros with ones, ones with zeros. So after inverting, so it is similar to 9. So let's check 0 0 1 1. So if you invert both of them, so 1 1 0 0. So we can say that 0 is complementing with 9. The similar thing we can see in the decimal as well. So that is why this is known as self-complementing code. So these two are examples of self-complementing code, XS-3 code and BCD code. And the last one in this numeric type is that error detecting and error correcting code. So in these two, we have an example, that is parity and Hamming codes. So what is meant by these things? So let's see with an example. So here we have some example, that is 0 1 0 0, that is 4. So if the computer or any device have some noise, so basically with the noise we can the computer signals may disturb. So if you have 4, if you want to transfer for a long distance, so in the transmission the last most digit, the least significant digit is changed as 1. So the overall output is changed. So 4 is converted as 5. So we don't need 5, we need 4. So this is the big error in the system. So for that, it is an error. So for that we have to identify that is an error and we have to correct it. So for that we have some codes like that Hamming codes and parity codes. So we are going to discuss in the upcoming video that. So this is the overall picture of the codes. So binary code is divided into two parts, numeric, alphanumeric. So again numeric is divided into subparts, weighted, non-weighted, sequential, cyclic, self-complementing, error detecting, error correcting. So in the weighted part only we have such two types, that is positive weighted, negative weighted. So we have saw all the examples. So we will discuss each and everything in detail in the upcoming videos. Thanks for watching up to now.